I am Mr. True. In this video, we are going to continue our discussion of transversals and the types of angles that are formed when that transversal comes through and cuts two or more lines. Now, in this video, we are going to be again talking about corresponding angles, alternate interior angles. We're going to be talking about alternate exterior angles, and then finally same side interior angles. Those are the types of angles that are formed when you have two or more lines being cut by a transversal. Remember that transversal has to cut or go through those two lines in two distinct points. In the previous video, we did all these definitions and explained and talked about these types of angles. But when those lines that are being cut by a transversal are parallel, as indicated by these two orange arrows, extra arrows that I've put on my lines, then a lot of really cool things happen. And thus we have what we got going on here. Now again, we have line L is being given that line L is parallel to line M. But in a geometry diagram, you're going to be looking usually for a pair of dark triangles that are added to those lines. And, you know, we always end lines with arrows, but there should be another pair of arrows highlighted on those lines somewhere to indicate that those lines are parallel. So if a transversal intersects parallel lines, well then we have corresponding angles. They are going to be congruent. Corresponding angles. When you look at this two intersection areas here, let's say in the upper left-hand corner of the first intersection area and in the upper left-hand corner of this second intersection areas, I have angles of 4 and 2. Well, instead of just saying 4 and 2 are corresponding angles, we're now able to say that they are congruent. Let me write all those pairs out for you. We have 4 and 2. So angle 4 is congruent to angle 2. We have angles 5 and 7, both in the upper right-hand corner. We have angles 6 and 8. And then finally we have angles in the bottom left-hand corner of angles 3 and 1. Okay, so I'm writing all of the possible pairs of corresponding angles and that they are congruent in this particular diagram. And by the way, we are going to do 4 algebraic examples, fairly simple examples, and then the last example in this video is going to be a proof involving two parallel lines being cut by a transversal and learning something about those angles and proving whatever, some facts that we're asked to prove. Alternate interior angles are congruent. Now, alternate interior angles. Alternate is, remember when we defined these in the other video, we want to go from the left side of the transversal to the right side of the transversal, or that alternate interior angles are on opposite sides of the transversal. And interior is the interior inside, in between those two lines that are being cut by that transversal. So this area in here is going to be the interior, and then outside these parallel lines that are being cut by the transversal, that is the exterior. So my alternate interior angles, which are congruent, are going to be the pairs of 3 and 7 and 2 and 6. So angles 3 and 7 are congruent, and now put a comma there. And what did I just say? 3 and 7, now 2 and 6. Okay. Now again, we have congruent angles, which means that their measures are equal. But if I were talking about measures, there'd be no congruency mark there. It would be the measure of 3, angle 3, is equal to the measure of angle 7. And that's what congruency means. Alternate exterior angles, where we're still going to alternate from one side of the transversal to the other, or be on opposite sides. Only we want to pick the pairs of angles that are outside those parallel lines being cut by the transversal. So now we're talking about 4 and 8 and 5 and 1. So angle 4 is congruent to angle 8, and angle 5 is congruent to angle 1. Okay, and again, like the 5, right side of the transversal, the ones on the left, and they're outside those two parallel lines. And then finally, same side. Okay, so we want two angles on the same side of the transversal, either both on the left or both on the right. and we want them to be interior angles. And those same side interior angles are supplementary. Let's not forget that supplementary means the two angles, the measure of two angles, add up to 180. Complementary is adding up to 90. So we're talking about 3 and 2. Those are both on the left and both on the inside of our parallel lines. And we have 6 and 7. So either one, we have the measure of angle 2 plus the measure of angle 3 is equal to 180 degrees. Or, if for some reason we needed to work on the other side, of course that was going to be the measure of angle 6 plus the measure of angle 7. Am I writing the right numbers? Yes. Is equal to 180 degrees. So, those are 4 types of angles and their properties when you are intersecting parallel lines and not just regular any old 2 individual lines being cut by the transversal. Again, we got 4 pretty simple, I hope, algebraic examples involving these types of angles, and then finishing with a proof. First 2 examples. Here we've got actually 4 parallel lines. We've got 2 parallel lines going horizontally, as best as I could draw it, and we have 2 parallel lines kind of going off at an oblique angle, a slant angle here. And we're going to need to find, in this question, we want to solve for both x and y. Now, if we got a lot going on here, and this is a more complicated diagram than how I started off with, so I want to first focus my attention on solving for x. And to do that, what we're going to do is kind of ignore part of the diagram, the extra stuff in there that I don't need really to solve for x. So if I cover up this portion of the diagram as best I can with my notebook paper here, we have 2 parallel lines being cut by a transversal. So what we look at here is if these are my 2 parallel lines being cut by my transversal, then I have 120 here and x over here. Well, you might want to call these same side exterior angles, but that's not one of the specific 4 types of angles that I gave you. Now, you might already know or think you know a relationship that's going on between 120 and x, but I want to use those 4 definitions that we have defined right now. So what that means is we're going to have to go through angle 1 because angle 1 and angle x. Now these are sort of, you see how they're both in the upper right hand corner of our intersection areas? So angle 1 and angle x here, these are going to be corresponding angles. So if I can figure out what the measure of this angle is, then I know what the measure of angle x is. Okay, so let's see, let's cover up some more of the diagram. If I cover up even more of this diagram, we see that this angle here, the 120 degrees, and this angle that I've put the 1 inside the corner, this is a linear pair. Okay, these are 2 adjacent angles who are forming a straight line. So, well, that is the definition. That is what a linear pair is. 2 adjacent angles whose non-adjacent sides form a line or opposite rays, if you will. So these are going to add up to 180 degrees. So we have 120 degrees plus the measure of angle 1 is equal to 180. We're going to subtract both sides by 120 degrees and get the measure of angle 1 is equal to 60. So if I go back up here and fill in some missing information now I know that the measure of angle 1 is equal to 60 degrees. Well, this angle and this angle, these are corresponding angles, and corresponding angles are congruent. So, if I know the measure of angle 1 is 60, then I can say the measure, or that x is also equal to 60 degrees because corresponding angles are congruent. Okay, so that's what x is, 60 degrees. And what we're going to do now is find out what y is equal to. Okay, well, as I look down here in this angle, which has a expression that involves y, I see 2 parallel lines here being cut by, now I'm going to be focusing on this part of the diagram. So let's once again cover up a little bit of this. I know what x is now, it's 60 degrees, so I could write that in there. So now I can kind of, leave out or take out some of my distraction here and look at this. I got 2 parallel lines as marked by the orange triangles I have here. I have two parallel lines being cut by a transversal. Well, in this intersection point, top right-hand corner, this intersection point, top right-hand corner, those are corresponding angles, and once again, if we're intersecting parallel lines, those corresponding angles are equal. So if these two angles are supposed to be equal, then I can say that 3y plus 6 is equal to 60 degrees. Subtract both sides by 6, moving away from the variable y, which we're trying to solve for. We get 3y is equal to 54. Divide both sides by 3 to undo that multiplication with the 3 and the y together touching. You're trying to undo, do the opposite math operation. So 3 divided by 3 is 1. And we get y is equal to 8. And let me just double check my work. And, oh, not 8. Good Lord, what am I thinking? 54. Let's see, how many 3's are in 5? Well, 1. And if I take a 3 out of a 5, that leaves me with 2, leaving me with 24. And 24 divided by 3 is equal to 8. I just remembered the last digit of the number instead of actually doing the math in my head. Okay, so that's the end of my first example, and I have my value of x and my value of y. Moving over here, this one is going to take less work. It's just a matter of a different looking diagram and, trying to, again, sort of ignore the extraneous information we need or we have. So let's see here. Like, I see that we have two parallel lines, and I see a transversal, this one coming up here. Okay, and this paper's not going to help me much. If I sort of cover this part of the diagram up a little bit and try not to get it all erased with my hand, I've got two parallel lines being cut by a transversal. Well, if I have two parallel lines being cut by a transversal, then my corresponding angles are congruent. Well, the 61 is sort of like in the upper right or in a sort of just above in this intersection. So is the y. So y, this angle here, and this angle with 61 degrees in it, those are corresponding angles. So the measure of, well, I guess we could just say that y is equal to 61 degrees because corresponding angles are congruent. Okay, now we have the x, and I still see my parallel lines, but angle x is not being formed by this line intersecting my two parallel lines. Angle x is being formed by this parallel line and this transversal. So since I've already figured out what y is equal to, let's do this. Let me take this transversal out of here. And do you see what's forming? We have two parallel lines being cut by a transversal. And let me just extend this line for a second. You see this Z shape right here? Whenever you have parallel lines being cut by a transversal, the alternate interior angles, if you can see that or maybe highlight it with a pen or something on your diagram that you've already made with a pencil, that Z shape is what is formed by your alternate interior angles, kind of like your Zorro. So the alternate interior angles, my parallel lines being cut by a transversal, this angle is above the transversal, this angle is below it. They're both inside the lines being cut by that transversal, so alternate interior angles are equal. So we have x is equal to 60 degrees. So really no algebra there, just a bit more of a complicated diagram and needing to sort of ignore the parts of the diagram that are not making the angles that we're dealing with and hopefully being able to recognize whether we have corresponding angles, alternate interior, alternate exterior, or same side interior. You might, I'm trying to think if an old textbook of mine used to call those consecutive angles, but same side interior angles. Let's get to the next two algebraic examples. Given line L and line M are parallel. Prove that angle 1 and angle 6 are supplementary. So we have two parallel lines, and the first line almost always in a proof is given. So yes, L and M are parallel, and that's given. Okay, so we have two parallel lines being intersected by a transversal, and I've just named all. I've just got a number in every single one of these angles. And we want to prove that angle 1 and angle 6 are supplementary. Now, 1 and 6, those are not any of the special four types of angles that we set up. They're not corresponding angles. They're not alternate interior angles. They're not alternate exterior angles. They're not same side interior angles. So we need to prove that they are supplementary. And of course, I've got a proof set up to work with you and help explain it to you. You could certainly come up with another proof and still have a perfectly nice sequence of logic and have a correct answer. So I'm going to give you a version or a proof. It's certainly not going to be the only one you could come up with. This one's very, very flexible in how many ways you could work it out. So I want to somehow link 1 to 6, and I need to link it through angles that we do know, corresponding, or alternate interior, or alternate exterior, or so on. So the first thing I thought of when I looked at this, and again, there's many, many ways you can approach this, is we're going to go ahead and match up 1 to 3. I somehow need to, I could match 6 to 2, I could go through the angle of 4, I could go through the angle of 3, which is how we're going to approach this, this proof. And regardless of whether you want to show a relationship between, or you can go to the 5, but I want to go with the 1 and the 3. Now, if I have angle 1 and angle 3, and I cover up the rest of the diagram that is not specifically related to those two angles, I see that angles 1 and 3 are adjacent and forming a straight line, which means that angle 1 and 3 are a linear pair. And that means that not only are 1 and 3 going to be a linear pair, but what does that mean? Linear pairs, a linear pair of angles, are supplementary by definition. So let's get that written for step number 2. Well, and you might want to say linear pairs are supplementary. Maybe your teacher's just happy with the definition of linear pair. Maybe they're just happy if you write linear pair. Talk to your teacher about what they want. Well, if angle 1 and 3 are supplementary, what does that mean? Supplementary angles are two angles that add up to 180 degrees. Let's get that written out. So a perfect example of when you build a proof, I'm already out of sequence from what I wrote in my notes. When you build a proof, all that's important is, like if I want to make a statement in line 6, it's probably going to need to be using information that I've built on in the previous statements of 2 and 3 and 4 and whatever. Some statements you can make at any point and it's perfectly fine, and other statements you need to pull from facts that you've justified earlier in the proof. So at this point I've made some statements and I didn't need to pull on any kind of knowledge or statements that have been made earlier in the proof. So at this point I'm just sort of stating facts. I haven't really seen a connection or a string of information that I need to put together. I'm just writing stuff down that I figured out. Okay, so I have a relationship between 1 and 3. Well, now that I have some kind of relationship between 1 and 3, we might not know really where it's going yet. Well, if I'm making statements about 3, we do know how 3 is related to 6. Now, ultimately, we want to prove something about 1 and 6, that they're supplementary. So I need to string those angles together through some other angle. And that now is going to be 3 because I've introduced it into my proof in lines 2 and 3. So we're going to say that angles 3 and 6 are congruent. And they are because they're alternate interior angles. And when parallel lines are cut by a transversal, the alternate interior angles are congruent. And I don't want to talk about 4 and 5 because they have nothing to do with ultimately what we want to prove. So I'm going to step out and say that angle 3 is congruent to angle 6. Okay, so alternate interior angles of parallel lines are congruent, and that means that angle 3 is congruent to angle 6, but ultimately I've got this equation up here that has a statement about measures, and I don't have anything about measures of 3 and 6 together, so just a small step, but what are congruent angles? Angles that have equal measure. Okay, well now we're at the point where the next line is going to have to build on information that I have justified and stated earlier in my proof. And if I look here, I've got the measure of angle 1 plus the measure of angle 3 equals 180. Well, again, the proof is about 1 and 6 being supplementary, or 1 and 6 adding up to 180. Okay, but down here I've justified now that the measure of angle 3 is equal to the measure of angle 6. So I can take my 3, the measure of angle 3, that symbol or that notation that's in this equation, take it out and plug in what it's equal to, which is 6. And now, do you see what's happening? I'm going to have one equation saying that with substitution, taking the 3 out and plugging in measure of angle 6, I'm going to have a statement that says the measure of angle 1 plus the measure of angle 6 is equal to 180, and that means I'm almost done with my proof. Very cool. Well, this is not what I'm trying to prove. This doesn't say exactly the same thing. This says the measure of angle 1 plus the measure of angle 6 is equal to 180, and I'm trying to prove that they're supplementary. But isn't that kind of the same thing? It's not formally in the proof yet in my sequence of logic, but it is what's coming up next. We're just going to say that measure of angle 1 and 6 are supplementary because, well, that is the definition of supplementary. Woo! Bang! There we go. Proof is done. Now, again, as we go through geometry, some people will get these proofs like boom, 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 and some people are going to struggle with them and maybe just always struggle with them. You need to make sure that you know your definitions, your postulates, your theorems right off the top of your head. Make an organized some kind of notes where the properties are on one side of the paper and actually what they say is on the other, and you can fold it and know them back and forth like that, or flashcards, something where you know those statements right off the top of your head. And as we do these examples, I am going to build these proofs from scratch and hopefully help you see the logic string. We have a complex problem, and there was, at least a few steps to get from point A to point B. And the real point of proofs is to help you develop those logical thinking skills of, hey, I've got this complex problem. How can I work it out and find a good logical sequence of steps that will allow me to complete the problem or solve the issue? You don't get that in a lot of classes. However, I do see a lot with the more of the newer books that they give you these proofs, and it's just like you're not given the reason, or you're given the reason and not a statement. That's more of, unfortunately, just a memorization type problem. It doesn't strengthen your sort of logic building skills. They're good examples, and you should pay attention to how the facts are stringed together to strengthen your own sort of logical problem solving skills, because that's really what you need to take out of these kind of problems once you're out of geometry. So, I'm Mr. True. Go do your homework.